Alright, so welcome to the Math 2413 Exam 2 review. Looks like there's a few people here. I waited a little bit in case some people were just trickling in, but we're just going to get started. The recording of this video will also be posted on YouTube, so anybody that misses it or is late could always look back on the video and then catch what they missed. So let's get started. Brian and I'm Qua, and Brian and I are the head leaders for this exam review. And we also have supporting leaders listed here. So this is just a review outline of the content that we're going to go over. So first we're going to do a topic overview for about 45 minutes-ish. And then there'll be like a 5-minute break for you to just like not have to think about math for a little bit. And then there'll be breakout groups to do practice problems. The supporting leaders will do a breakout room, and then the leaders will just go like they'll lead through the practice problems. So these are the topics covered on the exam. So it starts with like limit definitions of derivatives. You don't have to worry about the specific chapters, but that's just there for you to look back over the textbook if you are confused about any of the topics still. And these are the topics that are these are the topics that should be on the exam. We emailed the professor to verify the content, so ideally this should be correct. So it starts with the limit definitions of derivatives, and then once you kind of get through with that part, you don't really have to do it anymore, and then you do regular derivatives, and you just use derivative properties such as the chain rule, product rule, quotient rule. And after that, it gets a little bit less tangible with implicit differentiation, but with a little bit of practice, you can also get used to that. And related rates, actually, so everything builds off of the previous, and so related rates uses implicit differentiation, and that should be like the last topic that you cover on the exam. So feel free to say something if like you can't hear me properly or you have any questions. So the first section is 2.7 for derivatives and rate of change. Essentially, there are a lot of ways to say slope. There's instantaneous rate of change, there's derivative, there's tangent line to this, like tangent line, or slope of the tangent line. And these are the two main definitions to give you the slope at a specific point. So we have the definition 1, and then we also have definition 4 there. They basically will give the same answer if you use either formula, so each problem, whichever one you're more comfortable with. Let's see here. Yeah, so this is a practice problem. So I'm going to oh, this is a bit laggy. I'm just going to rewrite one of the equations. So limit as x approaches a of let's see here. I just want to make sure I use the right formula. F of x minus f of a. Yeah, okay. So I don't know why my tablet is lagging a little bit, but okay. I'm just gonna use my mouse. Why? Alright, so this is the formula for derivative at a specific point. Now, actually, this first problem doesn't specifically use that. It actually just does this part of the derivative. And essentially, like, you would plug in, like, f of 8 minus f of 4 over 8 minus 4. And that would give you, in this case, I think it should give you 0. And you would do that the same for this one, and this one, and this one. So essentially, like the next one, so this is part I. Part I gives you f of 10 minus f of 8 over 10 minus 8. And that's, let's see, so 1/2 times 10 squared minus 6 times 10 plus 23 minus And sometimes I like to put parentheses around so that then when you're subtracting something, you don't make a mistake with the negatives. So you would put 1/2 times 8 squared minus 6 times 8 plus 23 all over 10 minus 8 is just 2, so 2 there. And that should give, let's see here. I'm just going to plug that into a calculator, and then you should get minus 6 times 10. So it should be 6 over 3. Let me double check. So that should be that one. 10 squared minus 8 squared is 36 over 2 is 18. And then 18 minus, yeah, okay. So that should be 2. Oh, 16 over 2. Oops, yeah. 16 over 2, which gives 3. And then that's I, and then triple I gives you, what did this? I have no idea why my mouse is blinking like that. So f of 8. Oh, I skipped the, okay, wow. That's actually triple I. II, double II, is f of 8 minus f of 6 over 8 minus 6. And then that one should give, let's see here. I'm actually just going to pair things together. So it should be 1/2 times 8 squared minus 6 squared minus 6 times 8 minus 6. Okay, yeah, we're just going to skip these because it's just plug and chug. You're just plugging in a bunch of numbers. So essentially, you end up with, I'm just going to do these guys. So those ones are just plugging in. You're just going to average things. You're going to subtract. It's like the same thing as like that. Maybe this that you've seen. So y2 minus y1. Remember, the velocity is rate of change is slope. So it's very similar to this. And so part B is actually when you're taking a derivative. Mention. Oh, yeah, okay. So I don't know if you saw these problems on your, I think it's called DHW, but oftentimes they ask you to find an average velocity at like the range of like 8 to 10, and they do like 8 to 9, and then maybe like 8 to 8.5. So as you get closer to like a specific number and your range just gets narrower and narrower, this actually approaches like an instantaneous velocity. So for example, this guy should be closer than this guy to our instantaneous velocity. And similarly, this guy should be closer than the 4 to 8, because the 6 to 8 is like a narrower range. And as you get closer and closer to 8, so for example, like let's say 7.98, that should be fairly close to an instantaneous velocity. And so to actually do the instantaneous velocity, you do a limit where it actually gets infinitely narrow. You would plug in like f of t instead of f of x, and so you would have 1/2 t squared minus 6t plus 23. And then remember, a is 8, so we so we subtract 1/2 times 8 squared. So 1/2 minus 8 squared, or 1/2 times 8 squared. And again, I'm going to put a parentheses around here to not mess up the subtraction. So 1/2 times 8 squared minus 6 times 8 plus 23. And then you would divide all that by x minus 8. You just plug them straight into the equation, or t minus 8, sorry. So you plug that straight into the equation, and then you would take the limit as t approaches 8. Remember, x is your variable, but it could be really any variable. So usually it's x or t. And so when you plug this in, or I guess when you simplify stuff, you would get 1/2 t squared minus 6t, and then 48, right, 32. I'm just going to point this out. So 32 minus 48 is negative 16. And also notice how this 23 and this 23 should cancel. You should end up with a plus 16. And then that's all over t minus 8. And then, let's see here. If you multiply by 2 on the top and bottom, you should get t squared minus 12t plus 24 all over 2 times t minus 8. And then if you factor this, factorable? I don't think that's factorable. I'm messing something up. Something doesn't seem right. So it's always good to double check that you plug things in right. You get 1/2 t squared minus 6t plus 23. And then you have 32 minus 48, which is negative 16. But then there's a negative here, so that becomes a positive 16. And this is all divided by t minus 8. 24 is 32.
When you factor out 1/2, it becomes 16 becomes 32.
Oh, I can't. Okay, I can't multiply. All right. Sorry about that. Yeah, so then this factors to t minus 8 and t minus 4. So t minus 8, t minus 4. And the t minus 8 on the top and bottom should cancel. You should get t minus 4 over 2. That becomes t minus 4 over 2. And then when you plug in 8 into that, you end up with 4 over 2, which is 2. And so that should be your instantaneous velocity. And we did do, like, I'm sure now you know how to do regular derivatives. So if you do the derivative of s like normally, you would get t minus 6. And if you plug in 8, you also get 2. But when they ask these kinds of questions, they want you to use the definition of derivative. So, but you can always double check by doing a regular derivative. So that's the practice question for 2.7. And then 2.8 is also derivatives of functions, but at this time, you're going to be finding like the general derivative of the function. So over here is derivative at like a specific value. So this is at a. So if we saw earlier, this is like definition 4. And 2.8 asks you to find the general derivative of a function. And it's basically like the same idea where you would take a limit in the function and then you would simplify a little bit and then things would cancel out. So that one's pretty straightforward, and there's also like different notations here. The ones on the right here aren't very common, but these are fairly common, so you should use those. You use the secant slope 6, 8, and 8, 10 to get the instant velocity. Okay, yeah. Yeah, so there's other tutors that are able to answer questions, so I could answer it if it's like a very general one, but I can also help you with that. So derivatives as functions, there's also like the graphing aspect of things. So there's also like calculation stuff, but there's also graphing aspects. And there's like several types of points where you actually can't differentiate it. And one is like a corner, and it's like a point thing. So if it like abruptly turns a different direction, then it's not differentiable. Even though it's continuous, it's not differentiable. There's also discontinuities like jumps. So basically, if you see a circle with a hole in it, that means that there's a jump, and that's non-differentiable. It's also discontinuous. And if there's a vertical tangent, that's like an infinite slope, which means like the slope is like infinity, and so we call that non-differentiable. Sometimes you might think infinity is like a number, but it's not. So it's like undefined, and so you would consider that non-differentiable. So three types: bend, a jump, and then like a vertical tangent. And so here are some practice problems that you can look at. The first one is just asking you to point out which ones are non-differentiable. So you can notice that there is a corner here, there is a jump at 0, and then this isn't exactly vertical if you look very carefully, so I personally wouldn't consider that as a vertical tangent. So there's technically two discontinuities. Also, technically, if the graph isn't defined after a point, then it's also non-differentiable at the endpoints. So at -3, -5, and then at 4. And then that would be the same for any of the other functions. So in 42, there's a jump here and a corner here. So those are the non-differentiable points. And then in 43, this is a discontinuity. And even if these points were connected, which they're not, actually, I think the screenshot's cut off. So they're probably connected, which means that it's a corner. And then that will be non-differentiable. And then there's also a vertical line here at 5, so that's also non-differentiable. So you just have to keep noticing these things, and then as you do it, it's like pretty straightforward. There's only 3 types of points that are non-differentiable. And then the number 44, there's a corner here, so that's -2. And then this is a jump. Even though there's like 3 different points, you can still see that like it's discontinuous, and like there's still the open circles. So generally, if you follow that rule of thumb, you'll notice. And then at 3, there's also a corner here. Then for 26, we're asked to find the general derivative, so derivative as a function. This is once again using the definition of a derivative. But in this case, we're doing the limit as h approaches 0, right? As h approaches 0 of 1 over the square root of t plus h minus 1 over the square root of t all over h. So as long as you remember that formula, h plus h first, and then it goes h. And then you'll subtract them. Except, so one thing to keep note is that since those denominators are different, you can either find the common denominator, or you can multiply by square root of t and then square root of t plus h on the top and bottom. So what that kind of does is it gets rid of the fractions on the top, and then it just like adds like a kind of multiplication at the bottom, which you can kind of ignore usually. So you can just focus on the top. So we just like focus on the numerator, because the denominator just stays like a little bit complicated and you can't do anything until later. So we focus on the numerator, and we're just like, okay, so if you multiply by square root of t and square root of t plus h, and it cancels out the denominator for this one and leaves you with the square root of t. Then it also cancels out the other denominator, but it leaves you with the square root of t plus h instead. And then you're just like, oh, I don't exactly subtract these, but what you can do is you can multiply by the conjugate. And what that does is it gets rid of the square root symbols, but it does make like the denominator a little bit more complicated. We have square root of t plus the square root of t plus h, and then square root of t plus the square root of t plus h. So now the denominator encompasses this guy, and this guy. And the numerator actually will look like t minus the quantity t plus h. And so that actually ends up as negative h. So overall, we end up with, let's see here, I'm going to put it here, end up with negative h over h times the square root of t times the square root of t plus h times the square root of t plus the square root of t plus h. So it might look a bit overwhelming, but essentially you've just got a conjugate right here, and you just have two different square roots here, and you've got an h. Then if you notice, you can actually cancel out the h's, and you get -1 up top. So this denominator, remember this is under the limit as h approaches 0. This denominator actually gets pretty simple, because you end up with, I'm going to move this over here. So you end up with, as h goes to 0, you get -1 over the square root of t times the square root of t, because that h is 0 and that's square root of t plus h. And then you get square root of t, square root of t. And when things are alike, you can combine them, and then you get 2 square root of t. And then square root of t times square root of t is also t. You get t times square root of t, and there's also like a 2 in front. This is a t, and then that's the denominator, so it's -1 over that. And you could also rewrite that as -1 over 2t to the 3 halves, if you want to write it that way. So there's several ways to write it, but essentially it ends up as that. The things to remember are multiplying by a conjugate here. I'll highlight it a different color, but multiplying by a conjugate, and also getting rid of fractions, like inside fractions. So generally you don't want fractions in fractions, so you'll multiply by, like, just, I guess you could just multiply everything that's in, like, denominators at the top. So these two guys, and then that should get rid of all the denominators. It will make the overall denominator ugly, but it will make the top like more easy. So that's that one. Next one is, well, this is just more derivatives as functions. So this is like second derivatives. So remember, like d squared y dx squared is like just notation for taking the derivative of your first derivative. And then these are also different ways to represent that. An n indicates like the nth derivative. So this could be a 2 for the second derivative, or a 1 for first derivative. You could also denote it as primes. So these like apostrophes, essentially if you just have like 1 prime, then it's just the first derivative, and then 2 primes here is the second derivative. These are all, like these ones on the side here are all ways to represent the second derivative. So these are also some differentiation rules that you can use. Derivative of a constant is 0. Yeah. So derivative of a constant is 0. Derivative of x is 1. Derivative of c times any function is just, you can actually take out that c and then take the derivative of the function. And then the derivative of x to the n is nx to the n minus 1. So you just subtract 1 from the power. And then you can notice if like you set n equal to 1, and you have 1 times x to the 0, which is just 1. And then that's actually this property over here. So you can kind of notice how like properties get applied. Or actually, yeah, so you can notice things like that. What else? So this is differentiation rules. If you add or subtract functions and you take the derivatives of like that whole thing, you can actually just separate it and do each derivative individually. And this is just another property to know. Derivative of e to the x is just e to the x. This is itself. So it starts out kind of simple with like x's, and then you get e to the x, and this is just like another one you have to remember. So e to the x, and then also the power rule. So after you know your differentiation rules, I think someone has a question. If you have a question, you can just say it in the chat. But after you know your differentiation rules, you can do product and quotient rules. So this is where like everything just slowly adds up from each other. And with product rule, if you multiply two things, it's not as simple as taking each derivative individually. You have to kind of use this formula where you take one derivative and then multiply by the other function, and then take the derivative of the other function and then multiply by the first function. So you can remember it in different ways. I I think like derivative of first times the second plus derivative of second times the first. This is a really good format for doing these types of rules because it makes you significantly less prone to mistakes. So if you write down your functions, your first function and your second function, and then you write down the derivatives of those functions, all you have to do is just plug them in, and you can easily track down where you have made a mistake. Is there anything else important to say? I think that's all for that. Yeah. And then this is the quotient rule. So the quotient rule is a little bit more complicated than the product rule. One thing to note is like the subtraction here. And also the order does matter. So you have to take the derivative of the first and then multiply by the second. And you have to subtract the first times the derivative of the second. And then you have to make sure that your denominator is squared. This is just another notation for that. So instead of d dx, you do a prime, like a slash. What else? Yeah, so this is just the format that you use. So you can use this format for both product and quotient rule. It's just defining the things that will be involved, and then you just stick them into the formula. So Ashia, did you have a question? No.
Sorry, no, that was not bad.
Okay, that's fine. Let's see here. Okay, so that's product and quotient rule. And then this is a practice problem. I'm just gonna change. Actually, no, I think that's fine. So actually, part of this uses a bit of chain rule, which is later on, but you should know how to do that. So remember, if you're taking the derivative of something with a chain rule, you would take the derivative of the big guy, which kind of just stays the same, and then you would multiply by the derivative of the small guy, which is like times 2x. But that's not your full solution. It's always helpful to write down like each individual function. So in this case, let's do g and h because we have f as our original function. So let's set g equal x squared. H is e to the x squared. G prime is 2x. And then h prime is what we wrote over there using chain rule. You get e to the x squared times 2x. And then you would plug that into your product rule. And that would give, so derivative of the first, so 2x, and then you would multiply by the second untouched. And then you would add the first on its own times the derivative of the second, so e to the x squared times 2x. You could simplify, but like this is just getting the idea down. And then the other one's quotient rule, which is a little bit more complicated, but like again, you can define your variables. You're just like x squared, and the derivative of that is 2x, and then you got x plus 1, and the derivative of that is 1. So we put it in, and we're just like derivative of the first times the second minus the first, so x squared, times the derivative of the second. It's always helpful even to write like the 1. So even though the 1 like kind of goes away, it's helpful to write the 1 because it just makes you less prone to mistakes, and you can also track down where what you were doing exactly. And so this is what it would look like. You could simplify this, but this is like the general idea. That's incorporating quotient rule on the right here, and then product rule on the left here, and then also technically chain rule here. Yeah. And then, so this is a table of different functions that you could use. This showed like the CF, where you can take out the C when you're taking a derivative. You can also, it has the product rule, addition rule where essentially you can take the separate derivatives. And remember, this is using prime notation instead of d dx. It's just because it's less writing. This is e to the x. This is subtraction instead of addition. And then this is the quotient rule, shortened because you don't want to write f of x or g of x. We don't know if you have to simplify. Usually not, but yeah, it's always good to clarify. You can always just walk up to the professor during the exam and ask. Unless it's in the testing center, then it would be good to email your professor ahead of time. So the next thing is trigonometric differentiation. So these are the rules that you want to memorize. Like, they're really helpful. There's also like a few more. There will be like a table. Yeah, this. But you want to, like, you could technically derive some of them, but fundamentally you need to know that sine leads to cosine, and then cosine leads to negative sine. Yeah, they work the same with like chain rule, product rule, quotient rule, and let's see here. Oh yeah, so remember, if you see a 2, like sine squared of x, that indicates that it's actually like sine of x and then quantity squared. And then you also have to remember that, on the contrary, this is actually something entirely different. It's essentially, maybe if you don't want to get too confused about it, make sure that you always convert it to look like this instead. But you have to be careful with that. If there's ever a -1, then it's actually arcsine. It's an inverse function, which is different. It's never going to be like a -2 or a -3 because that's just like not how it goes. But if it's like a 2 or a 3 or a 4, and that just indicates like sine of x cubed or sine of x to the 4th. So -1 is the only like unique case that you have to be careful of. Yeah. So this is a practice problem. Essentially, this will be using a little bit of chain rule, a little bit of product rule. Yeah, so essentially, if you do the derivative, you would get 3x squared times sine of 2x. So remember, one of them goes derivative and the other one is untouched. And then you would write one of them untouched, and then you would take the derivative of the other one. But you also have to be careful because there's a 2x inside and not just an x. So there's actually a little bit of chain rule. And you take the derivative of the inside, which gives you 2. And then the derivative of tangent is just a property. It's just secant squared of x. Yeah. You could technically have applied like a identity rule to this, but like sometimes expanding stuff actually makes it more complicated. And you generally don't want to have to deal with more complicated things. So it's good to like just take the derivative right away and just use chain rule. So this has to do with trigonometric differentiation, but it's more so like when applied to limits. These are some limit properties that you have to, limit identities that you want to memorize. Essentially, sine of theta over theta is 1. Or both of these are for when theta is approaching 0. But sine of theta over theta is 1. Sine of like 100x over 100x also approaches 1 as x approaches 0. And what you have to make sure is that whatever is on the denominator has to also be inside that sine of x. You could have sine of like x squared plus 5x. Actually, I'm not sure if that one works. I think it should, but usually you won't have to deal with that. So usually it'll be something along like 5x, and then 5x. And then if the inside is the same as the denominator, then that should equal 1. And a lot of those limit questions that you'll have, they'll require you to like force these things to happen, which I think we'll be able to show in a bit. And so it's the same thing with the cosine. You could have cosine of 2x minus 1 over 2x, and that approaches 0. Yeah, so all of these, you have to make sure that your limit is going to 0. If it's going to infinity, it actually wouldn't make any sense because like a sine function goes like this, which means that it'll actually never converge to a thing. It'll just constantly go like this forever. So x shouldn't go to infinity. It'll but you do want to make sure that your limit is going to 0. Always check your limits to see what values. So as long as this is going to 0, then it works. I think also if they have something along the lines of like sine of x minus 1, it's doing the limit as x approaches 1. If they do something like that, you can notice that the top is going to 0 and the bottom is going to 0. And so that actually also works to be 1. So as long as it's a sine of something that's going to 0 over something that's going to 0, and those somethings are like the exact same form, then it should end up 1. And it's the same thing for the cosines as well. So this is an example. It might look like at first you want to do like cosine of 2x minus 1, and you actually might notice that that 2x squared is like 2x times x. So you could move that and be like, okay, you have cosine of 2x minus 1 over 2x and times 1 over x. But the thing about this is that your limit is going to 0. So it makes it a little bit tricky because this guy goes to 0, that's true. But also this denominator goes to 0, which means that the whole thing goes to infinity. So and infinity is like something that's like, infinity is like does not exist, right? And so you also have like 0 times infinity, which isn't something that is technically calculatable. So that means that's showing you that you did something wrong. And these questions won't allow you to use L'Hopital's rule, so you can't just apply L'Hopital's rule directly. You're gonna have to be a little bit creative with your solutions. And so if you're going along like this path and you're just like, okay, this isn't working, then you have to try a different identity. And in this case, there's the identity cosine 2x equals 2 cosine squared x minus 1. And if you apply that property, you end up with 2 cosine squared x minus 1 minus 1. So remember, I'm substituting cosine 2x. And then divided by 2x squared. And so that gives you 2 times cosine squared x minus 1 over 2x squared, which gives you 2 times negative sine squared. So that's another property that you apply. The cosine squared plus sine squared equals 1. And so this ultimately becomes, I'm just going to separate the limits, but like you essentially have a negative 1 that I'm just going to take out. And then you have a limit of sine of x over x as x approaches 0. And then you also have another limit of sine of x over x as x approaches 0. So that's just 1 times 1, and so your overall answer will be negative 1. So this one's a little bit tricky, but if you just apply different formulas, sometimes you can just blindly apply them, and then you can see which one would end up with something that you can simplify. But as you get more used to it, you can figure out which formulas to apply. Or like you can notice a dead end. You can just try plugging in numbers, and you're just like, wait, this isn't working. So always just try to see which formulas tend to work, and then you can always try different formulas if something else isn't working. Let's see here. So this is chain rule. So if you have some function that is like a composite function, so f of g, so there's like a function inside a function, then when you take its derivative, you can't simply just take like the derivative of one of them. What you have to do is you have to take the derivative of the big guy and then like keep the inside guy untouched, and then you multiply the derivative of the inside. So like for example, e to the x squared, the derivative would be e to the x squared, and then times the derivative of the inside, which is just 2x. And then this is Leibniz notation, which is just like another way to write down like chain rule. Essentially, you would like separate it into two things, and you can see how like those du's cancel out. But, like that's not exactly something that you have to worry about. Just remember how to apply it. So derivative of the big guy and then derivative of the inside. This is an example right here. So we've got a function inside a function inside a function, but it's not as scary. It's not as bad as it seems. So essentially, you would take the derivative of the big guy. So e to any power always leads to e to that power. And it also includes the derivative of the inside, which is actually just cosine of 2x. But wait, there's more. You also have to take the derivative of the inside of that, which is just 2. So the derivative of 2x is just 2. So that's that part. Again, you might have to simplify, you might not. But this would just be rearranging stuff because there's not that much to simplify. On this one, you decided to switch it up on you. And so you would do cosine, because the derivative of sine is cosine, and the inside stays untouched. Then you would multiply by something on the inside, which would be e to the 2x, because because powers of e don't change when you take its derivative. And then you take the derivative of the inside of that, which just gives 2. So, like, at least the way I think about it, I go here, this guy, and then I do this guy, and then I do this guy. You can go in whatever order as you want, as long as you're doing each of these individual parts. Some people like to start on the inside and then go bigger and then go bigger. But that's just personal preference. You just have to make sure that you're including everything. And then, let's see here. Okay, so implicit differentiation. Essentially, this is kind of like a conceptual being able to do chain rule. Essentially, you would take the derivative of both sides, and every time you encounter a y, you kind of do like a bit of chain rule. Oh, yeah, okay. So my partner is going to be doing 3.5 and on, so.
Okay, we'll just quickly switch, but as Qual was saying, I'll be leading till 3.9, but we're almost done. So as Qual was saying, implicit differentiation is just kind of an extension of what we've been doing so far. So if you remember, when you take a derivative, most commonly you see something like, let's have y equal to x. When you're taking the derivative, what you guys are actually doing is you're applying d over dx. So this means you're taking derivative in respect to the variable x, and you're applying to both sides. Normally we don't generally use this notation, or we don't really pay too much attention, is because when we take derivative of the left side, which is y, you actually just get dy over dx, which is f prime of x, and all the other notations, right? And this is what we most commonly see, because usually the left side y, dependent variable is always just y. And the other side just becomes, you take derivative, it's 1, and what you actually see is dx over dx, which cancels out to be 1, which is why you don't ever see something like derivative on the right side. In this case, when we change things, let's say you had something like x squared is equal to y squared. All right, minus 1. This is actually, or plus 1. This is actually the equation for a circle, right? So in order to actually differentiate these kind of equations, you notice that our y cannot be isolated totally. This is where implicit differentiation comes in. And so, as Paul was saying, when you implicit derive, you apply d over dx to both sides. So let's say we're doing on this equation, right? Equation for a circle. You apply derivative, so d over dx. When you're deriving any y expression, just like we saw here, the dx's are going to cancel, so you don't have anything there. You're just going to derive as normal. But for any y expression, you're always going to include dy over dx. And this is actually because of chain rule. So if you derive this one, it becomes 2x times over dx over dx, which cancels, plus 2y times dy over dx. So for every y expression derived, you need to include this dy over dx. once you do that, you isolate all your y primes, or your dy or dx. So you move all the terms. So in this case, you would isolate all the terms that have a dy or dx to one side, and everything else goes on the other side. This is just one. And then you isolate, or you solve for dy or dx. And in this case, that's going to be negative 2x over 2y. All right, and you would replace, if you're solving for the second derivative, any y's with your original, if you could solve for y, and or your y prime. And we'll see that in the second solution. So another kind of tips, right? This is what we just explained, that the dx, when you derive something, it cancels out to be 1. But when you're deriving any y function, you get something dy dx. Okay, so this is practice problem. Our task is to find the first derivative and the second derivative of this equation. So first we start, you're going to apply d over dx, which is just deriving both sides. So the left side becomes 2x plus, we're going to do the product rule. So the derivative of the first one is 1 times the original second plus the original first one, x, times derivative of y. And we know that derivative of y is 1, but it's times dy over dx. And then plus derivative of y squared becomes 2y. And any y expression will include a dy or dx. And it's equal to 0 on the left side, or right side. Okay, so if we simplify real quick, we get y plus x times dy over dx. And note that if you prefer, you can also use y prime as the equivalent, it's still a derivative, right? But I'm just going to use dy over dx for now. Okay. And then the third step would be to isolate all terms that have one of these dy over dx onto one side and everything else on the right side, or whatever side you prefer. And so in this case, we know we have these two terms. We're going to put them on one side, so we're going to keep them here. And then we're going to move these two terms to the right side. So that would be minus 2x minus y. And once you have this, you see that we can actually factor out dy over dx. And that becomes x plus 2y. And that's equal to negative 2x minus y. In this case, in order to solve for dy over dx, which is also y prime, you just divide both sides by whatever you have the sides factored. So many problems will kind of go like this, where you essentially implicitly derive both sides. You isolate your dy over dx, and you have to factor it out, and then you solve for dy over dx. In this case, our full solution for the first derivative is this. And note that sometimes, I don't know if it's going to be on your test, but if your question ever asks for explicit solutions, that generally means that they're looking for your derivative and only in terms of x. So in this case, this would not be an explicit solution, because in our answer, in our derivative, we have expression of y. In this case, if it's possible, if your original equation allows you to solve for some y expression, you can substitute it in. But in this case, because it's not really possible, because you get a plus or minus equation for y, well, we're not going to do it for this question. And plus, it also doesn't ask. Okay, so I'm going to make some room. To solve for the second derivative, it's the same thing. In this case, because we only have one side that's already the first derivative, all we need to do is take derivative again of just the right side, because this one will already be what we want, which is, in this notation, is d squared y over dx squared, which is also y prime prime. So if we take derivative, you notice that we have to use the quotient rule. So the derivative of the top is minus 2 minus 1 times dy over dx because it's a y expression. And that's the root of the top times the bottom. And just make some more room. And let me just continue here. Then you're going to find the derivative of the bottom, which is 1 plus 2 times dy over dx. And that's going to be multiplied by the top. And all of this would be divided by the bottom squared, x plus 2y squared. And in this case, in most cases, you're actually going to replace this dy over dx with what you found here, dy over dx here. And that would give you the full y prime prime. So in this case, we're going to replace all the instances of our first derivative with what we solved here. So that's going to be minus -2x minus y over x plus y. And all this is times x plus 2y minus 1 plus 2 times this big derivative minus y or x plus 2y. And then this is times minus x minus y. And all of it is divided by x plus 2y. So in a situation like this, I don't think you guys would be expected to simplify. So I wouldn't worry too much, but I would still ask your professor for clarification. Because it's so long and complicated, really, you probably wouldn't simplify in this case. But this is how they would like you to probably do it, because when you're finding the second derivative, they want you to replace the original dy dx with what you found here. Okay, so this is a helpful table if for inverse trigonometric derivatives. The reason why it's in this section is because actually I think they use implicit differentiation to actually derive these from the original equations, but I don't believe, I think I saw any problems that use these in your graded homeworks. But I would ask your professor for clarification if these are on the test. Okay. 6 goes to derivatives of logarithmic functions. Logarithms are the most common one you'll see is ln, which is technically has a base of e. Right, so logs are just the opposite of exponential functions. I'm sure you guys learned that before in previous courses, but derivatives of them, the most common one is ln, which is 1 over x. ln of any absolute value x is also 1 over x. And you'll actually see that the log of some base is equal to 1 over x times ln of the log base. And that's actually how the natural log one is derived, because if you take the derivative of it, you get 1 over x times ln of e. And because ln e is 1, that cancels to be just 1 over x. Now, this is one of the ones you will use for chain rule. Or you can just use the chain rule for this one, right? It's basically just saying that if there's any expression inside of a logarithm, when you derive it, you need to make sure you have that the chain rule on top, right? So it's like 1 over x squared plus 1 times the derivative of u, right? Whatever's inside. Okay. And so solving derivatives with variables and exponents, you might have seen something like this function, x to the power of x. Now the power rule, if you derive this, you actually would say, oh, can we just use the power rule? In this case, no, because the power rule only applies to x to the power of n, where n is some integer or some real number. Because x is a variable, it's not a real number, which means we can't use the power rule. So in situations like this, the process of solving these would be to quote unquote ln x both sides, which means you apply logarithms to both sides of the equation. You implicitly derive, that's what we had in 2.5, and then we isolate and try to find derivative that way. So in order to solve these, you would ln both sides and use this process, because we know that a property of logs is that if there's anything in the exponent of our whatever's inside, you can bring this out, and this would be equal to 2 ln x. And this is just an overview if you guys need reminders. And you can find this in the PowerPoint later. Oh, also, I forgot to mention that some derivatives might be easier if you do use the logarithm properties. And this is why you can also use this process. And we'll see in an example question. Okay, so this is one of the ones that will be easier if we use logarithmic differentiation. So if we ln both sides, we'll see that ln y kind of stays like this. And we can actually separate this one by using log properties. So the first one I'm going to do is I'm going to separate the denominator. We know that this one is equal to ln x minus ln y. Right? So this is minus ln of this denominator. And we know we can further separate this one because it's multiplied. We're going to get, in this case, ln of e to the negative x plus ln of cosine squared x minus ln of the inside. And we can further simplify because we know that ln of e will cancel out. We're going to get negative x. This one, we can actually put the 2 outside. So this will be cosine of x. And then this one stays the same. Okay, and then in order to find our derivative, we're going to differentiate both sides. So we differentiate the whole thing. And we get 1 over y. And because we derived an expression of y, we have to use the chain rule. We apply dy dx. The right side, now it's going to be much easier instead of doing the product rule and the quotient rule. We're just going to derive simply minus 1 plus 2 over negative sine. Oh, sorry. This should be cosine. Cosine of x times negative sine of x. That's the inside. And it's minus 1 over the inside times the derivative of the inside, which is this one. And I'm going to make a little bit more room. In fact, I might just make another slide. Okay. Let's see. Okay, let's just stick to this one. Okay, and once we get to here, we want to isolate dy over dx. So let's go here. And we're going to multiply y then, right? So dy over dx is equal to all of the side. Oh, I'll combine those actually. You get minus sine of x divided by cosine x. And that's minus 2x plus 1 over x squared plus x plus 1. And this is all multiplied by y. And in this case, if you want the explicit solution, which in most cases you will, you're going to have to replace this y with the original y, right? So we know the original y, in this case, was this whole thing. So in order to finalize our answer, we're just going to repeat what we had. And then we're going to multiply everything by our y, which is the original function that we got. Right, and so that's going to be equal to e to the negative x times cosine x squared x all over x squared plus x plus 1. Right, and this is where I would say you stop. I don't think you should simplify, because it'd be, or you should ask your professor for clarification. But in most cases, I think you want to simplify. You'd stop here. Okay.
Wait,
Yeah. Yeah, Asha. Yeah.
wait, can you go back?
Yeah. Yeah. Any questions?
No, like back.
Keep going.
Can you explain how you did ln of e to the power negative x. How did you just get negative x?
Okay, yeah, okay. So one of the properties, if you go back to logarithmic, right? If you remember, basically, ln of e, or in this case, we're using 4. ln of e cancels out, right? ln of e cancels out to be 1. We know that one of the properties also is that if we have ln of x to the power of anything, even if it's a variable, let's just say 5, we can bring it down first, right? So that'd be 5. In this case, let's try ln of e to the power of 5, right? In this case, what we're really doing is we're bringing out this exponent down. So that's 5 times ln of e. And we know that ln e is 1, so it cancels out to be 1. And so that's 5. So if we go back,
Oh, okay, that makes
the
sense.
reason why we canceled, right? Yeah, because this one, this exponent went down first. So negative x times ln of e. And the ln e canceled out to be 1. And so that's why it's this one. You can also just remember as, like, it will just cancel out. Just to be the exponent. Answer your question? Okay. All right, so this is another problem featuring a logarithmic differentiation. In this case, as we mentioned before, right? If we just use our basic differentiation rules, there's no way to really differentiate this one. We don't have any known rule that tells us, okay, if we have ln x in the exponent, how will we differentiate, right? We can't use power rule because this is not a real number, right? And it's not something we know. That's why we have to use logarithmic properties to pull it down so we can use another rule. So let's try it. We're going to ln both sides. All right, so ln y will be on the left. And in this case, because this exponent ln is within the exponent, we can bring it out. So in this case, we're actually going to bring it out as ln x, and this is multiplied by just ln of sine of x now. Okay, and once we have this, you'll see that now if we differentiate both sides, this is just the product rule. There's no rule that tells us we can't differentiate this now, right? So as before, this becomes 1 over y times dy over dx, and that's equal to this derivative, and this is just a product rule. The derivative of the first is 1 over x times the second, and that is plus derivative of the second, which is 1 over sine x, times cosine x, and that is times the original first, which is ln x. Right, and so we simplify a little bit. I'm going to also actually go ahead and multiply the y over. So if we isolate y, we're going to get, so this will be times y, so b times y, where we'll get ln of sine of x divided by x plus, and I'm going to put this cosine x over sine x into cotangent. That is one of the trig functions, times ln of x, and all of this is times y. And remember that if we want to solve for an explicit solution, we have to make sure this y is not here. In this case, we're going to go back to original. We know that y is equal to sine of x times the power of ln x. All we do is that we place this y with this function, without the ln's, by the way. So this would be sine of x to the power of ln x. And this would be our explicit solution and our answer. Okay, and we're going to skip over these since this is not tested. The last unit, before it goes into practice sessions, I'll try to go quick because we are running over time. The related rates, in this case, the hardest thing is probably set up the picture and set the equations, but the general process is to try to draw a picture of the situation and define what variables that they give you, realize what is constant and what is variable. And so in this case, let's say you had like a cylinder, right? And they're trying to give you some example, right? Like the height and there's water inside, when the water goes down, the height never changes. So the height is actually a constant, and they'll give you what the height is. But actually, sorry, that's wrong. The height does change. It's the height is the variable one, and the radius is constant because the radius doesn't change no matter how much water is inside the cylinder. So in this case, constants will be plugged in before differentiation. Let's say you're trying to find a volume. Volume of a cylinder is pi r squared times h, right? Let's say they're probably going to give us the radius because that's a constant. You'll plug it in. Let's say the radius is 1 squared times h. And this would be the equation that you're going to implicitly derive, right? Variables should be plugged in after differentiation. So you define, and then you do implicit differentiation, and you plug and chug. Let's move on to the practice question. In this case, example, air is being pumped into a spherical balloon. So we're going to have a sphere. So draw a picture, right, as best you can, along with all the variables that are needed, at a rate of 5 centimeters cubed per minute. So we know that centimeters cubed is a volume measurement. So our dV over dt is equal to 5 centimeters cubed per minute. Right, so we're going to write down all the variables. Determine the rate at which the radius, so rate is derivative, right? That's a radius of the rate, or rate of the radius means that you have a dr over dt. That means this is what we're trying to figure out, is increasing when the diameter of the balloon is 20 centimeters. So they give us diameter, but we know that radius is equal to 1/2 diameter. So radius is equal to 10 centimeters in this case, right? And so the volume of a sphere is 4 over 3 pi times r cubed. In this case, let's see. We know that our radius is what's changing. So in this case, we don't have any constants really. But we do know that when a balloon is being pumped, the radius will expand and change, and so will the volume. So in this case, we don't have any constants, right? So this is the equation we'll use. And we want to find it when the radius is equal to 10 centimeters. And we want to find d over dt. Right? So we want to know what we want to look for. If we implicitly derive in respect to time, you're going to get dv over dt is equal to 4 pi r squared. And because you're deriving by dt, you're going to have dr over dt. In this case, it's all just plug and chug. You have d over dt is equal to dv over t divided by 4 pi r squared. And we have everything we need. We have dv over dt and r squared, which is at 10. And you're just going to plug everything to find in the rate of change of the radius. In this case, we have 5 divided by 4 pi times 10 centimeters, or 10 squared. And this would give you the answer. I'm just going to leave it at that. You probably can have a calculator and calculate it, but I think I just want to move to the practice sessions. All right, and then the supplemental resources if you need it, which should be accessible in the PowerPoint. Okay, in this case, we have 45 minutes for the practice session. Sorry, we went a little bit overboard. Now we're going to split out to breakout rooms, and support leader and head leaders will help you guide practice problems.
Wait, so Brian, you're loading up the, okay, yeah. That's loading up the practice problems.
Okay.
Essentially covering, yeah.
So for the students who are here, is there any sections that you guys want to practice on? Or do you want to go through it like just one by one? Just name any like topics, and me or Kwa will probably work through it. So I'll just be scrolling, and then just comments if you have any. Okay, related rates. Okay. Gotcha. What, Kwa, you want to do the first one?
Yeah, that's fine.
We'll go switch to yours.
Okay. So I'm just going to share a blank whiteboard. All right, cool. So the question on the rates is, it asks for let's see here. Actually, let's see here. Yeah. So you have a paper airplane, and very important that you draw it correctly. No, I'm kidding. And don't use the whiteboard. All right. So we've got a paper airplane, and it is traveling horizontally. All right, whatever. Yeah, okay, you can see. So we've got a paper airplane, and it's traveling horizontally at an altitude of 20 feet. So got a paper airplane. And it's going at an altitude of 20 feet. That's and basically you've got 20 feet, and then it's also traveling at a speed of 90 feet per second. And then it's above a cat. We don't really have to care about what specific object it is, but it's above something, and it's 20 feet high from there. And they're asking what the rate at which the distance is changing, so the distance between the cat and the paper airplane are, when the paper airplane is horizontally 40 feet away. So I'm going to write that 20 feet over here. And you can clearly see that there's a triangle here. And it actually utilizes Pythagorean theorem. So this distance can be written as s squared equals, you actually want to keep as a variable because the x value actually changes. So remember, our paper is moving, but its height is not changing. This height remains constant. And so we have x squared plus x squared plus h squared. But as Brian said in the presentation, you want to put your constants in. And in this case, keep in mind that the altitude 3 feet remains constant. And the variable is like the horizontal distance from the plane to the cat. And so putting this in, we're just like x squared equals x squared plus 20 squared. And then whenever you're doing this, you do the implicit differentiation, and then you start plugging in stuff. You could plug in the x, and you would get 40 squared plus 20 squared equals s squared. And it does give a useful value. So you'll get s equals the square root of, if you just add them together, it gets square root of 2000. And what that tells you is that at 40 feet horizontally, you are the square root of 2000 distance away, like diagonally. And like, it is an important value, and it'll actually help us get the rate at which the distance is changing. And so in order to get that, you need to take the derivative. And if they're asking for rate of, if it's asking for like speed, then notice how feet per second, so feet per second is a unit like per time. So seconds is time. And so if it's per time, that indicates to you that you're taking a derivative dt. And what happens is, looking at this equation, derivative dt of that whole thing, s squared equals x squared plus 20 squared, that gives you, why is this whack? That gives you s times ds dt equals 2s times dx dt plus 0. Notice how this stuff doesn't change. Notice how like the squared doesn't change. And then like these two are very similar looking, but none of these will actually like cancel out. The 2's will go away, like the x over s times dx dt doesn't change. And so what I'm doing here is isolating the variable that they're asking for. So they're asking how the distance is changing at a specific point. And so that point specifically is equals 40 feet, and s equals, we calculated as 2000, square root of 2000. And then you might oh, I don't know what dx dt is, but actually they told you that the speed of the plane is 90 feet per second. So it's just 90. We can ignore units as long as every unit is like consistent with itself. And so we got 90 here. So what that ends up telling us is that we just multiply all that stuff or divide, and we're just like 40 times 90 over square root of 2000. And you would just put it into a calculator and then get like a specific answer. Let's see here. Oh, sorry. How's that? Yes. So one of them asked me to zoom in. Quickly just go back over what we were doing. So we were drawing a diagram, and we had a paper airplane that was moving, and it's 20 feet above a specific point. And I don't know, honestly, Microsoft Word is very weird with stuff, and it keeps like shifting stuff whenever I use it. But essentially, there's the 20 feet above, and they're asked about a specific horizontal distance away. But since the airplane is moving, you want to assign it a variable of x. And essentially, when asking a distance, you're usually using Pythagorean theorem because there's a height away from the ground, and then there's also a horizontal distance away from like a specific point. And so we have x, we have height, and then we have a distance. And the distance is calculated using Pythagorean theorem. So every time you see a triangle, just think Pythagorean theorem. And you would use that formula, and then you're given x and you're given the height at a specific point, you can actually solve for the displacement, the distance at a specific point. And then you would do implicit differentiation, and you would end up, well, implicit differentiation with respect to t. So you have to be careful not to do it with respect to x, because they're asking for like speeds, so speeds, and like if time is involved, then the derivative is with t, not with x. And when you do implicit differentiation, that ends up with like this equation, and like various things cancel out, constants go away, so it doesn't matter how big this is, it goes away. And you kind of just plug in everything that you've defined. They gave you the 40 feet away. They also calculated the square root of 2000 distance away, and gave you the 90 feet per second speed. And so when you plug them all in, that should give you the speed at which it's getting further away from the I guess Brian would do the ice cream problem.
Yeah,
So
I'll go
one
ahead and
other
do it. Or you guys want to do more related rate problems? I'm guessing that's it, yeah. Yeah, okay, gotcha. Okay, I'll bring it up, and then I'll go ahead and screenshot the problem. And let me know if it's too small or anything. Let's see, I should have the problem. Okay. Hold on. Okay. Just break the text here. 3.5? Yeah. Okay. Okay. So in this related rate question, the first thing I would do, as Qual kind of did as well, is draw a picture, right? So in this question, you're babysitting a child and they want ice cream. You buy ice cream cone with the ice cream, forming a perfect hemisphere with 2-inch diameter. So a hemisphere would be half a sphere, right, with a 2-inch diameter. So we draw a picture. This is the center. In order to access these questions, we will have it on our YouTube channel. Sorry, we can't really share files really good over Blackboard, which is why I have to do it this way. After this review is released, we should be like in a day at latest. all this material should be available in the description link for this review. And I'll give you the link if you need it. So check the YouTube channel for the review, and all these practice questions and answer key, PowerPoints, etc., will be in the description. Okay. Okay. I'll continue. All right. Let me know if you can't see too well, but I'll just try my best. Okay. So the answers will be pasted. Yeah, there's the answer key. Okay. So you buy an ice cream cone with the ice cream forming a perfect hemisphere. That's the hemisphere. Touch diameter. The child is picky and doesn't like the mint chocolate chip, which is unfortunate because that's a good flavor. Ice cream sadly melts at a rate. So when it says melts, you got to pay attention. We're not always going to give you the sign. In this case, because it melts, we know that the volume, so let's just first give a volume equation for a hemisphere. It's half of a sphere, which is this equation here, right? So the rate at which the volume changes is negative because it melts at a rate of 0.02 inches cubed per minute. Right, so pay attention to the wording. In this case, it's negative. When the volume is halved, so when volume is halved, at what rate is the radius changing? So in this case, we got to estimate our, or we got to find out what's at what volume there's radius, right? Because that's our independent variable. So in this case, we know that our radius is half the diameter, which is 1 inch. So therefore, our full radius when the ice cream is full is equal to 2 over 3 pi. I'm just going to leave it like this. And this should be in inches cubed. And so what we're looking for is that when the volume's halved, which means this would be halved, which would be 1/3 pi, then we got to figure out what our radius is. Right? And so in this case, we're going to put it back and plug it in again. And we're going to solve for the radius of ice cream where the volume is halved, which is this equation right here, right? So this is the volume of halved ice cream. And this is the volume equation to find out which radius it will be. So we solve for r. We cancel out these 3's. We can divide by, or we cancel the pi's as well. So let's get 1/2. 5/2, get on the side, is equal to r cubed. You do the cube root. And your r will be equal to, I don't think this is way to simplify, so it's cube root of 1/2. Right? And so this is our variable that we're going to use once we find out the equation that we need, right? Because we're looking for the rate at which the radius is changing. And remember, rate is always derivative. And because this is a real-life problem, it's going to be in time to time. So dr over dt. We're going to try to find what is our d over dt. So we know there's no constants in here. Radius changes as the ice cream melts. Volume also changes when it melts. So there's no constants. We're going to implicitly derive in terms in respect to t. And that's going to give us dv over dt is equal to, we're going to take derivative of this one, which cancels out that 3. So that's going to be 2 pi r squared. And because chain rule, we're going to have to implicitly put that dr over dt. And we're going to solve for d over dt, which means that d over dt is equal to our dv over t divided by 2 pi times r squared. So this is our equation that we have. And all that's left to do is to plug and chug. We know that this is what we're looking for. We have our dv over dt, that's given. We have r squared, which is what we figure out here. Okay, so we're going to go ahead and plug it in. We're going to get negative 0.02 divided by 2 pi times r squared. R squared, when the volume is posted, is root of 1/2, right? And so therefore, our radius is changing at a rate of, if you calculate this, let me go ahead and do that real quick.
Oh, maybe radius is squared too.
Oh, the radius is squared? Yeah. Sorry. Gotcha. So, sorry, I forgot that squared. Okay, then 2 pi times 0.5 to the power of. So if you guys are confused on how to calculate this thing, remember that you can transform into fractional exponents. So that'd be like 1/2 to the power of 3. Oh, sorry, not 3. It's 2 over 3, because inside exponent will be the top numerator over the root. So this is how the easier to calculate this. If you guys get calculators, it's much easier than trying to do all this. So that's how I'm going to calculate it. Okay, and I get -0, 0.005, 0.5, and make sure to write the units down. In this case, it's inches per minute. And how to figure out what like exponent is on here is because we're looking for the radius, and radius is in terms of one dimension, which means inches, right? So volume was cubed in inches, or radius is in inches. Right? So this is how this related rate problem. And the numbers don't work too well in this case, but it just means that this ice cream melts really slow. Okay, and you guys want to do 3.5? Well, do you want to take it, or do you just want me to keep going?
I can take it.
Okay.
So I'm gonna try a different application, but here. So this. So 3.5 is implicit differentiation, and we're just gonna do the first problem on the practice sheet, which is arctan of x squared y equals x plus xy squared, and they want you to find dy dx, which is almost true for implicit differentiation. Sometimes they'll ask you to get d squared y dx squared, but usually not if it's like super complicated. So in this case, we just want the first derivative. In implicit differentiation, you get 1 over x squared. Okay, so first, keep in mind that that the derivative of arctan of x leads to 1 over 1 plus x squared. So when you're doing this one, you keep in mind that you have the 1 over x squared y, and then that quantity squared. I'm going to rewrite it so a little closer. And also chain rule involved. But the chain rule is like also product rule. So sometimes I like to write it like this before I actually evaluate it, and then I'll evaluate it a little bit after. So it just makes things cleaner. And the right bit is a little bit more simple. So derivative of x is just 1, and then the derivative of x squared is, let's see here. Yeah. So the derivative of xy squared just uses product rule. You get y squared plus x times 2y times dy dx. And notice how there's the y times dy dx. That's because of chain rule. If you're taking the derivative dx of y squared, technically a function in a function. The y is a function, and then the squared is also like a function. So that makes it 2y times the derivative of the inside, which is dy dx. And right side, we didn't fully evaluate this yet, so let's do that real quick. Essentially, this is product rule, and you get 2x times y remains untouched, plus x squared times dy dx. This time x squared remains untouched. And so overall, you get 1 over 1 plus x squared y squared times 2xy plus x squared times dy dx equals 1 plus y squared plus 2xy dy dx. And you always want to pair things together. So whenever you're doing these kinds of problems, you look for every single instance of dy dx. And so I'm going to distribute this and move it over at the same time. Essentially, x squared over 1 plus x squared y squared minus 2xy, so I moved over this guy, and I combined these two guys together. And so that gets you the coefficient. That's what we would technically call that, the coefficient of dy dx. And then there's also the other terms. So I'm actually going to move this multiplied with this onto the right side. And so we're going to get the 1 y squared, that stays normal. And then we're going to subtract, so we're going to subtract 2xy over 1 plus x squared y squared. And then to get the final product, you just divide. And sometimes you would have to simplify. So you have 1 plus, I doubt it'll make you simplify, but I guess the best way to write it would be this. So you have your right side on the numerator, and then whatever you divided by on the denominator. And this should be right, but I'm going to double check it with the answer key. 3.5. Yes. Did I miss something? Oh, okay. So one thing you could do is multiply by 1 plus x squared y. Because having fractions with fractions is really ugly. And it looked bad, but it's actually not like the worst thing in the world. Essentially, you would have 1 plus y squared times, I'm just going to distribute it. So you can notice that this will FOIL with that. And you're going to get 1 plus y squared plus, I'm also going to turn this into x to the 4th y squared. X to the 4th y squared plus x to the 4th y to the 4th minus 2xy. So notice how the denominator cancels when you multiply on that. And so the numerator, so it's not as bad looking, still kind of bad, but it's not terrible. And then the numerator and denominator cancel, so then you get x squared, and then you multiply these two values, and you get minus 2xy minus 2x to the 5th y cubed. And that looks right. Yeah. So that's one. So we can also show another example of the other implicit differentiation problem is x squared plus 4y squared equals 4. And so this is an example of one where they'll ask for both dy dx and d squared y dx squared. And so it's like a multi-step process, but you kind of just do the same things, and it'll just add an extra step when you're trying to solve this one. So the first step is always taking the derivative. So you get 2x plus 8y times dy dx equal, so derivative of a constant is 0. And then isolate the dy dx. So we're going to move the 2x here, so negative 2x. And then we're also going to divide by the y. And this is also negative x over 4y. So it's always helpful to sort of like circle it, but not indicate that it's an answer, or I guess it would be an answer, but also it's something that will be used for the next part of the problem. So this, and then you move on to the next part of it. And you're just like, okay, so how do I get d squared y dx squared? Well, if you do implicit differentiation here, you immediately get 1 on the left, but the right gets slightly ugly. And also, like Brian mentioned in the presentation, you end up with negative 2x times 8 times dy dx. And this is minus. Yeah, so derivative of the first function derivative of the first function, and the second function is untouched, and then the first function untouched, and the derivative of the second function. And notice how there's no chain rule, because 8y, just 8 is a constant, so that can move out, and you would say 8 times the derivative of y, which is just 8 times dy dx. Let's see here. And yeah, so that's the numerator. And then if you're dividing, remember you have to divide by the denominator squared. I also, yeah, it's fine. I didn't use the simplified version, but like numbers will still cancel out. Whether you use this one or this one, it shouldn't matter. And then you might think you're done, but you actually have to plug in what value you got dy dx. So I'm gonna simplify as I go, but it's equal to negative 16y plus, so negatives cancel there, 16x times negative x over 4y all over 16y squared. And so notice these, they kind of just cancel on all of these. And you're left with negative y plus negative x over 4y over y squared. And then I kind of, again, you can multiply in order to get rid of fractions. Actually, you multiply by 4y. And then you would get, you should get, yeah, I think. So you should get negative 4y squared minus x squared over 4y cubed. Did I mess something up? I did mess something up. This 16 should be 64. Yeah. So this 16 should be 64. And so this would partially cancel into 4. And then, yeah, so then that 4 would go here. And we would end up with 16 down here. That seems right. Yeah. So then that would be your final answer. So now Brian can take over and do all of the remaining practice problems, even though there's nobody else here.